Okay, so by the time you've gotten to this screencast, I hope that you have kind of gone on the unit circle and done your degrees to radian conversions. One thing I want to show you here is what I did when I think about this is, you know, I went to 180 was pi, and then from 180 being pi, I just went to then 90 being pi over 2, right? And then if 90 is pi over 2, what's 30? Well, if 30 is 1/3 of 90, 1/3 of pi over 2 would be pi over 6, okay? Half of pi over 2 would be pi over 4, which is 45 degrees. And then 60 is just 2 of 30 degrees, or 2 pi over 6, or just pi over 3. And you may have observed this already, but you may notice that as you keep going up here and filling in the rest of the table, maybe you'll see something happening. Like 120 degrees, 120 is just a multiple of 60. 120 is 2 times 60. So in radians, 120 degrees will equal 2 times pi over 3, and that is exactly what 120 degrees is. Okay? And then we can go to 135 degrees. 135 degrees is a multiple of 45. It's 3 times 45 degrees. So 135 is just 3 pi over 4 radians. And then 150 degrees is, again, a multiple. 150 is a multiple of 30. 5 times 30 is 150. So 5 times pi over 6 is the radian measure for 150 degrees. And then I'm just going to go down here. I'll just go ahead and fill out the rest of them in a moment here. Okay, so what you'll see here is I just went through and just filled in the rest of the angles going all the way through. And one of the things that I hope you notice here is that when you're looking at the radian, the conversion from degrees to radians, I hope that you see that really, certainly remembering that 2 pi is 360, is very helpful, because this right here is the root of all of these. But in terms of quick recall, really all you need to memorize for fast recall are these two. 30 degrees being pi over 6 and 45 being pi over 4, because everything else is just a multiple of 30 and 45. All of these angles here are just a multiple of 30 or 45 degrees. So for example, when you've got something like 210 degrees, you know that 210 degrees is just 7 times 30 degrees. So 7 times 30 degrees is 7 pi over 6, because pi over 6 is 30 degrees, right? Okay, so 7 pi over 6 radians is equal to 210 degrees. Okay, similarly, if you're going from radians to degrees, if we have something like this, 5 pi over 4, well, this is just 5 times pi over 4, or 5 times 45 degrees, which is going to equal 225 degrees. Okay, so knowing these two pieces of information are really, really helpful. And you may not believe me right now, but in not so very long of a time, you will be able to go back and forth between degree measure and radian measure very, very swiftly. Okay? Okay, so now this brings me to a couple of thinking questions. I'd like to ask you 2 questions here. Okay, so here are the 2 questions, and maybe you'll just copy them down and then think out loud with me, or actually even better, why don't you see if you can see if you can think through the answer on your own, then replay me. Okay. So number 1, which one is greater? Theta is pi degrees, or alpha, which is pi radians, right? This angle is pi radians. Well, this is interesting. Pi radians, is 180 degrees. And theta equaling pi degrees, this is an angle with 3.14 degrees. And if you visualize a 3-degree angle versus a 180-degree angle, then the greater angle is alpha. Which is greater, cosine of pi over 4 or cosine of pi over 4 degrees? And I will say we're going to answer this question without a calculator, using just what you know from the work we've done in trigonometry so far. Go ahead and try and think about that. Think about this and replay me. Well, cosine of pi over 4 we know is 1 over root 2, or radical 2 over 2, right? And 1 over root 2, depending on your estimation, 1 over root 2 is maybe about 1 divided by 1.6 about, okay? And then we're here and you're saying, gosh, how do I figure out the cosine of pi over 4 degrees? What do I do there? How would I even think this through? And let me help you. Well, first of all, this is the cosine of 45 degrees, right? Cos of pi over 4. Cosine of pi over 4 degrees? Pi over 4 is about what? Well, pi over 4 is about 0.75 degrees. So the cosine of 0.75 degrees? Whoa, how do I think about that? Well, there's a couple of things you could do. I mean, you could think about, you could think about, if you wanted to, you can superimpose unit circle if you wanted. And you could maybe in here put an angle in standard position and take a look at the cosine of 45 degrees, which, as we've done, maybe you've dropped an altitude, and we have this right triangle. And if this angle right there is 45 degrees, I know that the cosine is going to be this length over the hypotenuse, right? Which is exactly 1 over root 2. And maybe you'll think to yourself, well, let's see if I can draw another circle here. And let's do a 0.75 degree angle. Oh my. And that's even bigger than 0.75, but you get my point. And maybe let's think about the same thing, superimpose a right triangle there. Oh, interesting. And if you look at here, this is the angle of 0.75 degrees, the adjacent over hypotenuse is very close to 1, right? And then I think to myself, well, I know the cosine of 0 degrees equals 1. So the cosine of 0.75 is going to be close to 1. And being close to 1, like 0.999, is bigger than 1 over root 2. So this is the greater value. Okay, that's just some thinking questions. Okay, the other thing I want you to think about is this. How about, I just thought of a third question. Okay, this one. Order these angles from smallest to largest. Okay, are you ready? And this one I'm going to have you do as part of homework. I'm curious to see what you come up with. Okay, order these angles from smallest to largest without a calculator. Okay, and I'm curious to see what your answers are. All right, now I'm going to move on, and I'm going to talk about this now. Oh no, here we go. Converting between degrees and radians. So for these angles up here, the conversion, we just figured out the conversion. 360 degrees equals 2 pi, and that gives us all of these here radian measures of their corresponding degree angle measures. What I want to think about today is, how do you take, an angle like, I'll just think of, let's say 82 degrees, okay? How do you convert that into an angle in radians? And this should be a fairly comfortable part of this pencast. Well, I'm going to talk about the number 1, okay? Just remember, the number 1, someone in the class said, is often in disguise. I can't remember who it was. It may have been Daniel. Daniel with the booming laugh. Number one can sometimes be in disguise, and I think the example that he may have given was like 4 over 4 or 2 over 2. That is 1 in disguise. But 1 can also come in these disguises. 1 could also, why is this in here? 1 could also come in the form of 12 inches over 1 foot, right? 1 could come in the form of, let's see, 2 cups over 1 pint. The important thing here is that in these ratios, fractions, what have you, I know you'd see 12 divided by 1 and say 12 divided by 1 equals 12. 2 over 1 is 2. And you are right. But we're not talking about 12 divided by 1. We're talking about 12 inches over 1 foot. Okay? 2 cups over 1 pint. When you take into account the units that are involved, these are also 1. Okay? And another 1 is this, 180 degrees all over pi radians. That is also the number 1 because, again, different units, but same entity. And similarly, pi radians over 180 degrees is the number 1. So when you're looking at 82 degrees, the question is, what form of 1 can I multiply by that will leave me with the unit of radians and cancels out the degrees? And this, by the way, it's stoichiometry. Stoichiometry is literally just translates to unit conversion, which you probably did in chemistry. Okay, if I multiply it by pi radians over 180 degrees, you'll notice here then the degree units cancel, right? And I'm left with 82 pi over 180 radians, which of course can simplify to be 41 pi over 90 radians. So 41 pi over 90 radians is equal to 82 degrees. Okay, that's how we convert between degrees and radians. Okay, and finally, what I want to do is, as I've said all along, I have been very purposefully, deliberately weaving in and out of functions, review of functions, reviews of algebra with this introduction to trigonometry, and that is on purpose because one of the things that we're getting used to this year is a course that is rolling cumulative. What that means is that any assessment we have can cover everything that we've done over the course of the year, which is a very, very grand endeavor. And I will talk a great deal in class about how to make that easy and doable for you. For us, okay? But that is one of the reasons why I'm weaving back and forth between the two. So I am going to switch gears here and talk about a function that you haven't seen probably since last year. It's not going to be the polynomial function. The polynomial function you've not seen ever. And what you've seen so far with polynomial functions, which include quadratic functions and linear functions, is that polynomial functions have a domain of all real numbers. Polynomial functions are smooth. Polynomial functions are continuous. And we talked about multiplicity of roots. We talked about end behaviors. We talked about sketching a curve. Okay? I just want you to remember and revisit, just recall for a moment. Okay? Not polynomial functions. Exponential functions. Now, exponential functions are not polynomial functions. It doesn't mean that exponential functions won't share some of the same characteristics as polynomial functions, but exponential functions are not polynomial functions. So, for example, okay, f of x equals 2 to the x is an exponential function. Right away you'll notice the defining feature of exponential functions is that the independent variable x is in the exponent. Okay, you would never see that with polynomial functions. Here you may remember that the base, that which is raised to the x, is the number 2, and since that base is greater than 1, this is an exponential growth function. Okay. And maybe I'll ask you now to go ahead and sketch this graph. Go ahead and sketch it. And maybe I'll do it with you if you completely and totally forgot. You can do a little t-table in your head. One thing I want to ask you is this question. I'm going to ask you this question here. As x approaches positive infinity, comma, f of x approaches what? As x approaches negative infinity, comma, f of x approaches what? Okay, let's see. Well, 2 to the 0, anything to the 0 equals 1. Okay. When x equals 1, I have 2. When x equals 2, I get 4. When x equals 3, I have 8. So I'm kind of off the charts here. 1, 2, 3, 4, 5, 6, 7. Okay. And then when x equals negative 1, 2 to the negative 1 is 1/2. When x equals negative 2, 2 to the negative second is 1/4. X equals negative 3, 2 to the negative third is 1/8. And what I see here is this situation. Here is kind of your classic exponential growth function. As x approaches positive infinity, what does f of x approach? As x approaches positive infinity, f of x just grows larger and larger. F of x approaches positive infinity. As x approaches negative infinity, what does f of x approach? Really important. I want to underscore this. Approach. Notice I did not write equals. Okay. I don't want to say what f of x equals. What does f of x approach? What does y approach? Y approaches 0, actually, if you look here. See how close the curve y approaches 0, but it will never get to 0. In fact, you may remember that what exists here, this horizontal line is a, yes, good job, this is an asymptote, okay? Exponential functions have a horizontal asymptote. Horizontal asymptote. Asymptote. At, I like to be in the habit of giving the equation of the asymptote. Okay? All right. How about just right now, what I'd like you to do is sketch the following. Okay? Go ahead and sketch this function. Labeling any critical points. So y-intercept, label 2 other points, label as many points as you need to generate a reasonably accurate graph, label any asymptotes that may occur, and then replay me for the answer, please. Okay, so in this picture here, as you'll see, I graphed the y-int 0, 6. Here's 1, 2, 2, 2/3. Ooh, here's -1, 18. And yes, I know my scale is off. Okay, y equals 0 is the horizontal asymptote. Because the base here, right, this base, that which is being raised to the exponent, is between -1 and 1, or it's less than 1. This here is an exponential what, everyone? Yes, an exponential decay function. Okay, so I just wanted you to remember what exponential functions looked like. In general, what can we say about exponential functions, everyone? What could we say about exponential functions? Are exponential functions smooth? Yes, they are. Are they continuous? Yes, they are. Do they have a domain of all real numbers? Yes, they do. That all seems in common with polynomial functions, right? Those characteristics. However, what's different about exponential functions is this asymptotic behavior. There's a horizontal asymptote. And I'd like you just to make sure that you visually recognize, like, oh, this is what a typical exponential function looks like, a growth or a decay. But all exponential functions will have, and you can go ahead and list them, will have a domain of all real numbers, okay? Domain of all real numbers. They will have smoothness, and they will have continuity, and they will also have a horizontal asymptote. Okay, All right. So what I'm going to have you do now is to go back to the calendar and look at step 3. So step 1 was book homework, step 2 was watching this screencast, and step 3 will be a problem set that relates to this screencast. Enjoy your drop day tomorrow, Friday, and I will see you on Monday of next week.